Hello, everyone. So, about 2 weeks ago, this happened in production for the primary key of an important table. Yes, we ran out of numbers. I'm sure several people here have had the pleasure of this problem. The primary key of this table used the int data type, and the biggest value you can represent is around 2.1 billion. Once you reach this value, you can't insert any new rows. As you can imagine, this is a problem. It turns out there is a data type bigger than int, perhaps unsurprisingly called big int. So that's a simple fix, right? Let's just alter the table schema. We worked out the throughput is around 15,000 rows per second per core. And we have around 2 billion records. So 2 billion divided by 15,000 records per second is about 30 to 4 hours, give or take. Fortunately, we pay AWS wheelbarrows of money for our database and have 48 cores. So we ran the migration, and it was beautiful. We could utilize all the hardware available to us, and we got the migration done in a couple of hours off peak. Actually, that wasn't what happened at all. Postgres, for all the awesome things that it enables, actually has some pretty sharp edges when it comes to big data. If we ran this migration, it would execute on a single core, and the company would have been out of operation for several days. As you can imagine, this was unacceptable, so we had to solve the problem by breaking it down into several jobs. But dealing with such a problem makes you think, what kind of properties do we want our software systems to have to avoid scalability issues? Efficiency is really important. It's scary when you have 2 billion records and find that even simple operations take a huge amount of time. The difference between 2 times slower on small data might be between 5 and 10 minutes of execution time, which probably wouldn't cause any problems. But for big data, it could be the difference between 40 and 80 hours of execution, which is significantly longer in absolute terms. Responsiveness is also very important. The aforementioned migration blocks all other access to the table. It would literally prevent the business from operating for several days. How we choose to build systems and the latency of operations within those systems greatly affects our users. Finally, being robust is another important property. As systems scale in size and complexity, errors become the norm, not the exception, and handling these errors as part of normal operation is necessary for the correct and reliable operation of a system. So that's what I've been working on for the past 2 weeks. And it's a great case study for talking about asynchronous Rails. So hello, my name is Samuel Williams, and today I'm going to talk about asynchronous Rails. It's a real pleasure to be here. So let's start with the basics. What is synchronous execution? In the database migration example I talked about, Postgres creates a new table with the updated schema and copies the records across one at a time. When it's done, it replaces the old table with the new table. Here is a visualization of that process. We see the original table and the temporary table with the updated schema. We copy the items across one at a time in order. Each item is copied one after the other, and we're done when all the items are copied. At this point, we can swap the tables. This is an example of synchronous execution. The time it takes is the sum of all the individual operations to complete an order. Actually, while I was waiting for coffee this morning, I started thinking about the same problem. Asynchronous execution, in contrast, means execution without synchronization between the individual steps. If those steps can be executed independently of each other, we can potentially interleave or overlap the execution, thus reducing the total execution time. In the case of the Postgres migration, you could subdivide the problem into multiple chunks and copy each chunk independently. If we use 2 processes to copy rows, we could potentially reduce the time of the operation by half. Because we know in advance how to divide the work into independent chunks, no coordination is needed, and the 2 operations run independently of each other, in other words, asynchronously. However, in order to complete the operation, we do need a synchronization point, where we wait for all the individual jobs to complete, so the total time depends on the slowest sequential job So if we can break the problem down, we can reduce the total runtime. We haven't yet defined how to execute multiple jobs asynchronously. There are two main ways in which you can execute multiple jobs. Parallel execution is normally accomplished by having distinct processing units work on independent jobs. Most modern processors have a lot of cores, and each core can handle one job at a time. But as we saw earlier, if you don't break your work down into separate jobs, you won't be able to take advantage of all the cores. Concurrent execution is another way to execute asynchronous jobs and allows us to improve the utilization of a single processing core by interleaving execution. For example, if a job is waiting for data from the network or local storage, another job can execute. Alternatively, jobs might have a fixed maximum time slice so that each job gets an opportunity to execute. Practically all modern computer systems are both parallel and concurrent, with multiple processor cores interleaving the execution of multiple jobs. So, what are the advantages of asynchronous execution? Let's consider both the advantages of application performance and the advantages to application design. The first and most obvious advantage of asynchronous execution is that it allows us to improve application performance. As we saw, the synchronous execution model was limited to a single processor, but by breaking the problem into separate asynchronous jobs, we were able to improve the algorithm to take advantage of all the available hardware resources, thus giving us better scalability. In addition, by splitting up the work, the total execution time can be reduced, lowering the latency and making your application more responsive. The second area that can benefit from asynchronous execution relates to application design and the kind of problems we can solve. We are no longer limited to synchronous request-response style execution models for the user experience and can leverage asynchronous operations to enhance interactivity of the application, including multi-user experiences. Similarly, with real-time updates, users can receive timely and relevant information, enabling applications to provide a continuous stream of data. It's also true that some problems can't be solved at scale with a single sequential processor in a realistic time frame. Some problems are literally impossible to solve without huge data centers with tens of thousands of processors each solving a chunk of the problem. Asynchronous execution enables us to solve scalability problems and unlocks new user experiences. But why does this matter to Rails? Rails is a framework for building web applications and naturally benefits from asynchronous execution in a number of ways. In order to understand how Rails benefits from asynchronous execution, let's consider a single request. Firstly, we will focus on Ruby, the language and environment which executes all the code, then Rack, which defines the interface that servers adhere to for handling HTTP requests, and finally Rails, which provides the framework for building your application. Firstly, let's talk about the changes we made to Ruby to provide a foundation for asynchronous execution. One of the big bottlenecks in a lot of web applications is I/O wait. This manifests in things like databases, where you send a query over the network and wait for the results to come back. Depending on the complexity of your query, you could be waiting a long time. It's also common for web applications to do HTTP requests. Connecting to remote services, sending the request, and waiting for the response can easily be hundreds of milliseconds. A lot of background job processing systems use Redis for enqueuing work. This involves sending a message across the network and waiting for an acknowledgement. Here is an example of a real web application which does all of these things. At its peak, 25 milliseconds is spent executing Ruby code, the blue part, and 150 milliseconds is spent waiting on I/O operations, the yellow and green parts. So, can't we just make Ruby faster? Here is the proportional time spent executing Ruby, which took 25 milliseconds, versus waiting on I/O, which took 150 milliseconds. So what happens if we make Ruby 10 times faster? Well, because Ruby was only a small proportion of the total execution time, the advantage is not that huge. The total request time was reduced by about 15%. What about if we could improve the performance of Ruby 100 times? It would be a huge effort to improve Ruby's execution performance by 100x, and yet at best, in this case, it can only improve the latency by about 15%. This is why it's important to characterize performance issues before attempting to address them. As an example of this, we have been working and continue to work on improving the performance of fibers and threads. Between Ruby 2.6 and 2.7, I introduced native coroutines and improvements to fiber allocation. We made it about 3 times faster in general. We also did something similar for thread, reducing thread allocation costs by about 4x. But unless all your application does is allocate fibers and threads, you won't see a huge advantage from these optimizations. At best, you might get a 5 to 10% reduction in latency. So, how do we reduce waiting time? Well, let me be more precise. If network operation is going to take 100 milliseconds, we generally have to wait. But while we are waiting, how do we improve utilization? We need a way to interleave the execution of multiple jobs so that when one is waiting, another can execute. It turns out we have this already. A fiber can execute a block of code, and at times we choose, for example, when we know we have to wait, we can suspend its execution and resume a different fiber. By using multiple fibers and an event loop, we can convert synchronous execution into asynchronous execution and reduce the total execution time by interleaving the execution of the individual jobs. In 2017, I experimented with and created a gem for fiber-based concurrency called async. Version 1 uses wrappers around Ruby's I/O objects to switch between fibers when an I/O operation would otherwise wait. Compatibility with existing code was tricky because they used the native Ruby objects rather than the wrappers I created in the async gem. So in 2018, I introduced a proposal for what is now called the fiber scheduler, to add hooks to Ruby so that we could intercept the operations that could wait. And this allowed us to be more compatible with a wider range of existing code. The fiber scheduler proposal was merged in 2020 and was supported in async version 2. From the user's point of view, the code executes sequentially, but the fiber scheduler delegates waiting operations to an event loop where they can be executed concurrently. So let's talk about the different operations that we hooked in Ruby. One of the first hooks we implemented, and possibly one of the most important, was waiting for network sockets to be readable or writable. Here is a small example of an HTTP request using async and the fiber scheduler. We use the async block to define tasks which can execute concurrently. Internally, each task has a fiber for execution. Everything inside the task executes sequentially like normal code, but the task itself executes asynchronously in relation to other tasks, using a shared event loop. We can use the fiber scheduler interface to redirect the blocking I/O operations like connect, read, and write to the event loop. Notice that we don't need to use any special wrappers or keywords. Depending on the host operating system, async uses highly efficient multiplexing provided by KQ, ePOL, or IOU ring. This allows us to interleave multiple tasks that are waiting on I/O. Being able to integrate with existing code was also critical to the success of async, so we made all thread primitives safe to use within the fiber scheduler. One of the most important operations, joining a thread and waiting for it to complete, can be delegated to the event loop when running on the fiber scheduler. Here we show 3 threads being created. Each thread sleeps for 1 second to simulate external work. Then we wait for that work to finish without blocking the event loop, which we expect to take around 1 second in total. We also support thread mutex, which can be used to implement safe asynchronous access to shared resources. Here we compute the Fibonacci sequence using a thread and an asynchronous task, which have access to the same state. Here is where the thread reads the previous 2 values and computes the sum within a synchronized block, and here is where the event loop does the same operation. The asynchronous queue is another important tool for building scalable programs, and it's okay to use in the fiber scheduler. You might want to communicate between different parts of your program using the producer-consumer pattern. Here we have a thread that adds several items to a queue, and those items are subsequently consumed by an asynchronous task. Most network clients need to perform DNS resolution, and the standard libc DNS resolver is blocking, so it can be tricky to support asynchronous DNS queries, but we introduced a hook for this too. Almost any program which interacts with the network will need to resolve a host name to an internet address. Any Ruby code that does a DNS resolution will go via the fiber scheduler hook, which in async uses Ruby's own resolver library. Resolving addresses is asynchronous when done within the fiber scheduler. It's also common to launch child processes and wait on them, so we added a hook for this too. This hook is used by a variety of different methods, including the system method, backticks, and process wait. Here we have an example that launches 5 child processes, each sleeping for 1 second. Since they are all in separate asynchronous tasks, the total execution time is only a little bit more than 1 second. We also introduced safer timeouts. In Ruby, the timeout module is often regarded as unsafe due to the fact that it can interrupt code at any point. However, when running in the scheduler, only operations which yield to the event loop can raise a timeout error, which is somewhat more predictable. In this example, we put a timeout of 1 second around a sleep of 10 seconds. Both the timeout and the sleep are hooked by the fiber scheduler. The timeout will cancel the sleep after 1 second and safely exit with the timeout exception. So, with the hooks provided by the Ruby fiber scheduler, we can improve the concurrency of existing Ruby programs without any changes. It appears to execute sequentially, but it is internally multiplexing between fibers using an event loop. This is a huge achievement, and I'm really proud of it. One other area I'm excited about is asynchronous state handling. With parallel execution, it was relatively easy to deal with a per request state. Each request runs until completion, and it's impossible for state to be interleaved. In this example, at the start of each request, a thread local is set to a request ID number. With concurrent execution, we need to be very careful to scope per request state to each individual fiber. Lots of existing code assumes the former sequential execution model. In this example, each fiber is assigning a thread local, but because the execution is interleaved, when the first request is resumed after request 2 sets it, it has the wrong request ID. To solve this problem, we introduced per fiber inheritable storage. Each fiber has an associated storage, which can be considered per request. When you create nested fibers or threads, that state is automatically copied, which allows you to easily and conveniently share context and data between nested asynchronous jobs. This greatly simplifies Ruby programs that need to use this kind of state. So, Ruby now provides the foundation on which we can build asynchronous applications. The next critical layer is RAC, the interface between the web server, like Unicorn, Puma, or Falcon, and your application framework, like Rhoda, Sinatra, or Rails. RAC is a gem which provides convenient code for building web applications, and a specification which defines how web servers should invoke web applications. For a long time, RAC-based servers only supported HTTP1. RAC itself is loosely based on the CGI specification. So while this made sense given the circumstances when RAC was created, it also became an obvious limitation as I worked towards supporting HTTP2. Here is a small example of a RAC application. You can run this on any RAC-compatible server. It takes any request and returns a 200 OK response with the plain text, "Hello world." RAC 2, which is the most popular release of RAC at present, has limited support for bidirectional streaming. HTTP, since its inception, has actually had full support for bidirectional streaming. It's unfortunate then that RAC did not expose this. In particular, RAC's lack of direct support for streaming has made things like WebSockets particularly challenging to implement. In September last year, we released RAC 3, which is probably best described as a stricter subset of RAC 2 with mandatory support for bidirectional streaming. Bidirectional streaming is probably the most important feature of RAC 3 because it makes it easier for web applications to take advantage of asynchronous execution. For example, improving interactivity or reducing latency. That doesn't mean it wasn't possible with Rack 2, it's just a lot easier and better defined with Rack 3. Here is a simple hello world example. We create a body proc which accepts the stream argument, writes to it, and then closes the stream. We respond with the body proc, which we will refer to as a streaming body. The web server will execute this proc with the underlying HTTP connection as the stream argument. We can do more advanced things like streaming templates. In this example, we create a small template which sings the traditional 99 Bottles song. Between each line, we sleep for 1 second while generating the output. We can return this template as a streaming body that writes to the output stream. The streaming response can be easily demonstrated by an HTTP client, like this. Each line is printed after a 1 second delay. Because the templates are generated and streamed in real time, the time to first byte can be greatly reduced. Here's an example of how to use WebSockets, which is compatible with any Rack 3 server, which includes Falcon, and recently with Puma's 6.1 release, is compatible with Puma as well, which is just blows my mind. It's awesome. So this adapter takes a Rack request environment and generates a suitable response using a streaming body. The implementation itself just echoes back every incoming message. Anyway, making this easy was a really important goal for Rack 3, and I'm looking forward to seeing what people do with it. Rack 3 can also help reduce memory usage. Buffering large datasets can require a lot of memory. Multiple requests with pagination are sometimes used to avoid these issues, but ultimately result in more complexity. Incremental streaming of large datasets can simultaneously reduce latency and memory usage. Here is an example showing how to stream CSV data using the Rack 3 streaming body. We wrap the output stream in the CSV interface. Then we generate rows of CSV data. The streaming CSV can be easily seen using the command line HTTP client. Since we only generate one row at a time, the memory usage and latency is limited. Rack 3 also makes it easy to implement server-sent events. If we want to stream real-time events to a web browser, server-sent events are a good option. This protocol was first specified in 2004 and supported by browsers starting in 2006. It's an excellent choice for real-time events like chat messages, stock market tickers, status updates, anything you want updated in real time. On the server side, you generate a streaming response of type text event stream. We write events one per line using this format. We can implement some client-side JavaScript to receive these events. We create a new event source object and listen for all messages with a callback function. We append messages to the document in the callback to show them being received. Then if we open this page in a browser, we can see the streaming events. It will automatically reconnect if disconnected, and it's far easier to use than WebSockets, so I highly recommend it. With the introduction of Rack 3, how do we ensure that all servers implement the new functionality correctly? The Rack specification has a middleware that validates how applications should behave, but it does not provide any mechanism to test servers. I wanted to encourage servers to adopt Rack 3, so I created RackConform, a test suite for server implementations. RackConform provides an application and a test suite around the server being tested, and validates the requests and the responses. It's not hugely extensive, but includes tests for Rack 2, Rack 3, and new features like bidirectional streaming. As you can see, all the tested servers pass the Rack 2 level conformance, while Falcon, Puma, and WebRick pass the Rack 3 conformance. Anyway, this has been a great tool for helping server maintainers adopt Rack 3. I just mentioned Falcon, which is my own web server that I created based on async. It has full support for HTTP 1, HTTP 2, Rack 2, and Rack 3. Since Falcon is built on async, it provides fiber-based concurrency, which is different from Puma's thread pool-based design. So let's compare Falcon with Puma. Both servers are capable of handling more than 10,000 requests per second, which is absolutely excellent. This synthetic benchmark generates small responses of about 1,200 bytes. You can see they both perform well. The more response data we generate per request, the less requests we can handle per second. This benchmark generates large responses of about 12 megabytes each. At the rate of 200 requests per second, that's about 2.4 gigabytes per second, which is close to saturating a 25 gigabit network link from just one Ruby process. This might seem pretty decent, so why should we prefer Falcon over Puma? To answer that question, let's look at what happens when we introduce a blocking operation. Here is a small application that simulates a blocking operation, for example, a database query. We use a predictable sleep to reduce the variability of the measurements. Each request sleeps for 1/10 of a second, so you'd expect about 10 requests per second per connected client. Puma is able to use all 16 threads to handle about 160 requests per second. However, Falcon has an advantage, since it can interleave the execution of all the requests. In this benchmark, I actually connected 100 clients, and Falcon was able to serve them all, while Puma had some timeouts. We can see this advantage in the real world too. After porting an IO-bound project to Falcon, without any code modifications, it shows outstanding concurrency. I think that speaks volumes about how important concurrency is in modern web applications. Rails version 7.1, which should be released soon, is on track to fully support Rack 3. So how do we change Rails? I'll touch on a few of the pull requests that have been merged over the past 2 years. One of the most tricky things in Rails is the ossification of request per thread. A lot of internal systems use thread local variables, or were actually accidentally fiber local. And as we talked about before, if we are concurrently interleaving fibers, you can end up with state leaking between requests. Rails introduced a new interface, isolated execution state, that can be configured for either request per thread or request per fiber, and allows Rails to work correctly on Falcon, which uses the request per fiber model, while still being backwards compatible with existing applications that might depend on request per thread. One particular area where this was a problem was the per thread active record connection. Since the connections were shared per thread, it was entirely possible to open a transaction in one request fiber and see that transaction still open in a different request fiber. By using the isolated execution state interface, it was possible to fix the connection pull implementation so that it is safe to use active record in Falcon. Rack 2 specifies that the request input body should be rewindable. That means it can be read multiple times. However, to do this, the input body must be buffered, and buffering the input body can consume a lot of storage. It can also increase the latency if it's buffered completely before passing the request to the application. Very few applications made use of this buffer, and it's also at odds with real-time streaming. So in Rack 3, this requirement was dropped, and so we need to update Rails accordingly. This is still a work in progress. setCookie is one of the most unique headers in HTTP, in that it's the only header in which multiple values can't be merged into a single field using commas. Rack 2 separates multiple value headers like this using the newline character, but Rack 3 prefers to use an array of string values, which is easier to manipulate, safer, and more memory efficient. The Rails test suite also assumed the internals of the Rack 2 format, rather than the HTTP semantics. So we implemented setCookie header parser, which follows the HTTP semantics, and updated all the relevant tests to use it. This makes it compatible with both Rack 2 and Rack 3. In addition, Rack 3 requires all header keys to be lowercase and stored in a hash table. Surprisingly, this wasn't actually the case in Rack 2. This is to make it more efficient to implement middleware and modify response headers. This is also the normalized form in the HTTP specification and a requirement for HTTP 2. Because there is a lot of code which assumes mixed case for header keys, we've introduced a class, Rack Headers, which implements lowercase normalization with case-insensitive key lookup. Rails has adopted this as part of the controller layer to avoid compatibility issues. Rack 2 had a lot of code related to rack the specification. Rack 2 had a lot of code unrelated to rack the specification, and it was hard to evolve rack the specification independently from rack the implementation. Specifically, we have extracted code into two new gems: rack session, which includes a convenient implementation of session management, and rack up, which includes a convenient way to run a rack application. Rack session in particular suffered from several security issues that cut across multiple releases of rack. By extracting it into a separate gem, it will become easier to update independently of rack. These gems are compatible with both rack 2 and rack 3, so they are now integrated into Rails. This will allow us to evolve these specific areas of rack more rapidly and independently from rack the specification. What database adapter can I use? Unfortunately, not every native library is compatible with the Fiber scheduler. However, this problem is solved with a bit of effort. In short, the best option right now is Postgres. The PG gem has built-in support for fiber-based concurrency, which when combined with the per-fiber isolation level in Rails, just works like you'd expect. If you are using MySQL, GitHub has just released a new library called Trilogy, and an active record adapter which supports the Ruby Fiber scheduler. I've heard rumors that this will be released as part of Rails 7.1. That would be very exciting. So with Rails 7.1, you'll be able to use Falcon and Rack 3 to gain some interesting new capabilities. How do you take advantage of this in your application? Actually, this was a trick question. You don't need to change anything. The Fiber scheduler provided by Ruby transparently improves the concurrency of your application. Rack 3 makes it easier to build asynchronous applications, and Rails continues to evolve with these underlying changes. So in summary, Ruby 3.2 provides a great foundation for asynchronous programs, and in particular, concurrent execution. Rack 3 provides a standard interface for bidirectional streaming, enabling things like WebSockets without escape hatches. And Rails 7.1 is compatible with Rack 2 and Rack 3 and allows web applications to take advantage of these new features. And that's just the beginning. We've built the foundation for you all. Now it's up to you to go and build awesome asynchronous Rails applications. I'm incredibly excited to see what you all create, and I'm incredibly proud and privileged to be part of it. Thank you for listening to my talk, and please feel free to ask me any questions or come and find me later.